This presentation concerns the climate analytics hub that we're developing at CMCC to address various use cases such as the multimodal analysis. And can you still see the slides?
Yes, we see.
Okay, I have some. Okay, I'll just give it like this. Okay, so just start briefly with the main motivations behind this analytics hub environment. So let's consider, for example, the multimodal climate analysis, which is one of the main case studies of this analytics hub. In this case, this type of analysis requires access to various datasets from intercomparison experiments, such as the SNP data, and made available through the ESGF node. So this type of analysis is very challenging since it requires access to dataset from multiple models. So the typical workflow that the user would do would be first to download the necessary data from various data nodes, and this of course can take some time due to like network issues and also like latencies and so on. And then once that once the download is completed, the user typically creates his own homemade scripts and has to install or update the tools when not available, and this could of course be quite burdensome. And moreover, these tools are typically sequential or with very limited level of parallelism. So this could lead the scientists to develop a very user-specific solution in order to achieve a higher degree of parallelism. And then finally, not all scientists have access to HPC and storage infrastructure. And while this type of analysis would strongly benefit from using systems and tools able to scale over large data volumes. So the analytics hub tries to address these issues, and it provides an open data science environment, mainly providing computing and analytics capability. It builds on top of the Earth System Grid Federation data node, so it provides centralized location to run multimodal climate analysis. And so this provides a more variable-centric approach with respect to the model-centric and distributed approach from the Earth System Grid Federation data nodes. So I said this analytics hub is built on top of a data collection layer, which pre-stage and cache the necessary data sets from various ESGF data nodes, and then keeps this data synchronized with respect to the remote copy. And of course, this centralized approach is not able to scale on the entire SNP data archive, but multiple analytics hub could be deployed, each one serving different variables in order to address into a single location the computation for the specific variables. So this slide shows more in detail the architecture of the analytics hub. It consists of several tools and services. And in the slide, there are some examples of tools that we're deploying at CMCC. So the upper layer provides a graphical user interface, which allows the access to the virtual environment. And this could be, for example, the well-known Jupyter Hub. Then there is a wide set of high-level Python libraries for data analytics and visualization, and it also provides a front end for the execution of heterogeneous jobs and workflows. It includes various high-performance data analytics frameworks and machine learning frameworks to scale the analysis over the computational resources. And the data collection layer is implemented through Cinda, which downloads the data and keeps the copy of this data synchronized. It also includes a monitoring system based on Grafana in order to track the application execution, also the resource usage. And then, since one of the goals of the analytics hub is to target open science, we also include some services for data publication, such as opened-up threads and shared repository hosted on GitHub in order to share code and results and foster the usability. The ENES Climate Analytics Service is one of the an implementation of the Analytics Hub. This is being developed in the context of the EOSCAB project by CMCC and DCARD-Z. It aims to provide a data science environment in order to support the scientists in their daily research activities. It is one of the EOSCAB thematic services, and it builds on top of the OVIA data analytics framework and integrates other components from UDAT and EGI. In the context of the project, it has been integrated with various services and also into the EGI federated cloud infrastructure, which is quite a nice feature that we implemented. And EGI provides a Jupyter interface so it can be easily and freely accessed by users by simply using a web browser. It integrates a wide set of Python data science modules for data analysis and visualization, such as NumPy, SciPy, Pandas, but also Basemap, Matplotlib, and so on. Moreover, we also included a wide set of training and demonstration material in the form of Jupyter notebooks, which we found to be very useful for this purpose. Ophelia is one of the main components of the Analytics Hub. It's a CMCC foundation project targeting data intensive analysis. It provides a high performance data analytics framework by joining high performance computing and data analytics paradigms. It provides server side in-memory based engine for executing analytics and I/O. And it also provides an end-to-end mechanism in order to run complex experiments in the form of workflows. The communication with the server side can be achieved by using various tools that we provide Ophelia. So we have the Ophelia terminal, which is a rich shell-like command line interface that can be used to interact with the Ophelia server, and the Ophelia, which are the Ophelia Python bindings. So the interaction is started by the user, which sends his commands by using one of these tools to the Ophelia server, which in turn orchestrates their execution on the computing infrastructure. And this can also be done in parallel. Each operator is applied on a data cube, and it creates a new data cube, so that this allows for views of intermediate results. And this is also, the system also tracks the data provenance. In fact, besides data processing operator, Ophelia also provides data management operators. This slide shows a subset of the operators that are currently available. We have about 15 operators, and those which are more related to the data processing are mostly parallel. And this allows, for example, for data import and export from into files, or for time series processing, or for data cube reduction or subsetting, intercube, but also provide some metadata management operators, which are sequential. And this provides, for example, for data cube and file system management, for data provenance, and for data exploration. The DiPaola Feeder class, which I mentioned a couple of slides ago, provides a more programmatic interface to interact with the Ophelia server. It handles the all client server interaction. It can be easily integrated with other Python modules and into Jupyter notebooks. It can be easily also installed locally, since it's available on the main Python channel, such as the Python package index, or through Anaconda on the Conda4 channel. It provides two complementary classes: the client, which is able to submit any type of command in a more query-like structure, or the cube class, which introduces the data cube abstraction to manage virtual data cube objects, which are pointed to the data which is stored on the server side infrastructure. So since the analytics hub is composed of several services, we also included a Grafana monitoring system in order to track the resource usage, and also to provide the application. In fact, some of these services, such as Ophelia, could also be running in parallel over multiple compute nodes, and in turn this could be run by multiple users. So it's very important to understand what's going on the computing infrastructure. So we integrated this real-time monitoring system, and designed a couple of dashboards in order to track different type of metrics. So, for example, infrastructural metrics, which are shown in the top right part of the slide. And this includes information such as CPU usage, memory usage, and disk, and also some application metrics, which are on the lower right part of the slide, which show the execution of the operators in Ophelia, their status, and the progress of the workflows. So now I would like to show a brief video. I'm not sure if this can be, it is clear enough. Anyway, this video shows the implementation of the precipitation trend analysis. This is done into the Jupyter interface through this Jupyter notebook. And as you can see here in the top left part, there's the definition of some parameters which concern. I'm not sure if the quality is.
we don't.
Can you see the video? I'm not sure if it's the quality.
Not really, but anyway, the time is about 15 minutes. So please.
Okay, yeah, so I'll just skip this and go right to the conclusions. Okay. So to conclude, the Analytics Hub provides a variable-centric environment for data analysis, and it allows to overcome some of the barriers like created to download and setup of the environment, and provides a user-friendly and accessible environment for the development, test, and execution of the experiments. And as next steps, we aim to implement new multimodal experiments, and also to integrate the Analytics Hub with the new CMCC supercomputer. And okay, so thank you for listening.